All right, let's get started. All right, everyone, welcome back. So just one thing I want to point out, there's been talking going on during class. Please do not talk. People do not learn as effectively if there's other distractions in the room. So if you're talking, I'm going to stare at you until you stop talking. Okay? All right. So just want to address that. But anyway, won't get the exam back yet. I still have some folks who are missing, need to make up the exam. So I hope to get back to everyone by Thursday with the scores updated as well. Okay? All right. Are there any general questions? Yes?
The quiz on Thursday, that's on the
IR. Yeah. So the quiz on Thursday, IR. So use the lab we did a few weeks ago. Make sure you can answer all parts of the questions we asked, okay? So no mass spec, don't worry about mass spec. IR, so if you're given an IR spectrum, can you identify what types of bonds are present? And can you suggest a structure if provided the chemical formula? Could you write up or draw a structure that could match the IR spectrum based on the key peaks you pick out? Okay, you do not need to memorize the IR numbers. I will provide you with those. Okay, so no need to memorize those, but you need to be able to interpret an IR and use the information given to you to suggest a structure or tell me what type of bonds are present. Okay, and remember, IR, they don't all look the same, so you have to practice. Okay, so I think those spectra, those handouts I gave you give you a lot more practice, much more than you may need. So if you can do all those, you'll be in good shape. Yeah, Captain.
For when we have this material on the exam, will we have to memorize the IR numbers for that part?
No, you'll be provided with it. Yeah. All right. Any other general questions? Yes.
Were the exam grades like the same as the last exam?
I haven't finished grading them yet, so I can't speak to that yet. But we'll see. Okay. All right. Any other general questions before we begin? If not, I'm going to talk about attendance. Today is the 14th, almost halfway through October. It's already week 11. We were talking about, me and Dr. Dykes, Simone, we're talking about how fast it has gone by. Okay, time just goes by. All right. So last time we talked about alkenes. So remember the alkenes, E1. So I just wanted to go over a little bit about the alkenes here. Why are more substituted alkenes more stable? Okay. So imagine we have this scenario. We have a generic alkene here. So let's write our alkene. So all right, so like I said last time, do you remember which one's more stable? Not the one on the left. The one that's more substituted. So look at the alkene, right? So if you have more carbon groups attached to the alkene, that's the more stable. And it's very similar to why radicals are more stable with more substitution and carbocations. All right, it has to deal with this thing called hyperconjugation. Okay, so hyperconjugation is an interesting phenomena. Without getting into it, it's usually called no bond resonance. Let me explain. All right, so look at this double bond here. So here, the double bond, right, it has p orbitals, right? And if you draw the molecular orbital for this double bond here, there's an orbital here that can interact with the groups around it. This is called the pi star orbital. So the pi star orbital, well, I want to get at, you don't have to reproduce this, but this is the reasoning behind my blanket statement. Like, how do you know it's more stable? What does that mean, right? This is the reason. All right. So pretty much in chemistry, what's most important, other than partial charges and reactivity, what's most important in chemistry is orbitals. All right. That's why we talk about them so much. We learn so much about them in 1A and 1B. That's kind of the whole foundation of how chemistry works. All right. So this is our pi star orbital. Okay, so a pi star orbital is very high in energy. So if it can interact with another orbital of lower energy, you get the most stabilization, and that's MO theory in a nutshell. Okay, so here is our LUMO here. All right, this stands for lowest unoccupied molecular orbital. Sorry, I wrote that a little too fast. That's molecular. Okay. Now, as drawn, these hydrogen atoms, what do you think? Are they perpendicular to the orbital, or are they in the same plane? These hydrogen atoms we just drew. So here's one plane, right? And here's another plane. So now, are those p orbitals, remember, p orbitals, they go above and below a plane, right? So I think they're above and below this arrow. What about these hydrogen atoms? Are they within the same plane? Yes. So these hydrogen atoms are perpendicular to the p orbital. They cannot interact with it. Okay? So here we have no stabilization. Okay? CH bond is at 90 degrees to the p orbital, okay? So that's the p orbital, or the molecular orbital, the pi molecular orbital that has the p orbitals, okay? Now, if we add a carbon group, now that the hydrogens, the carbon-carbon bond outside of the alkene, it can rotate. And so now the hydrogen bonds are actually not in the same plane, and they can overlap with the p orbital. So now let's draw this other one here. All right, so the same picture really is going to apply. So notice here I shaded the orbitals opposite from the lobes on the p orbitals. And that's because this is an anti-bonding orbital. They shouldn't have any bond density or electron density between the two orbitals, because that would indicate if you occupy this, you should have no bond being formed. And the fact that this LUMO here is empty indicates that there's no, there should be a double bond because this one is empty, okay? So we still have the H's here. But now one of these carbon atoms, okay, we can actually draw its hydrogen here. Okay, and then we're just going to keep the other two hydrogens like that. All right. So it doesn't matter which hydrogen you use, and this could actually be a carbon-carbon bond as well, as long as there's a atom bonded to this exterior carbon atom. There's going to be this positive interaction. Okay, so we still have the LUMO here, so this is still the pi star. But what happens here is this is a filled orbital now. So we're going to draw this molecular orbital for the hydrogen and shade the bottom lobe. And we see here there is an interaction between this sigma bond. So the sigma CH bond is going to interact with the pi star. And when you do that, a similar example you would get, here's your sigma bond, and here's your pi star. All right, here's the pi star. It's empty. The sigma bond here, so here's the sigma CH. Okay, so this is the pi bond of the CC double bond right there. There's 2 electrons in this bond, okay? And it'll interact with this pi bond here. And what you get is a lower energy interaction. And the 2 bonds go here, okay? So now what we have formed is a new MO. So this is our, now, I'm not going to call it a bond because you're not actually forming a new bond 100%. It's just an interaction, okay? So these 2 interact, and they lower the total energy of this whole molecule, all right? And that's what, that's why this is more stable. So if I have more, if I have more substituents, what does that tell you about the relative stability here? More stable, because you have more of these interactions, all right? So this is what we call, so the more, right here, more sigma CH slash CC to pi star. So I'll just point an arrow here to indicate they're interacting. So more of these interactions, the more stable you are. The more stable an alkene is. Okay, so that's what stability is. Here you have just ethene is less stable than a primary one, which is less stable than di-substituted, okay? Or it could be any order really. And then less stable than tri-substituted, less stable than tetra-substituted. Okay, when we talk about alkenes, we'll talk about cis and trans, how they relate in stability. But this is the order of alkenes. So more stable, sorry, not more stable, least stable. So least stable, most stable. And how we quantify stability here is we hydrogenate, or basically get rid of the double bond and add 2 hydrogen atoms to each of those carbon atoms. The one that releases the least energy is considered the least stable. If you release more energy, that means you weren't stable to begin with, so your reaction is more exothermic, so that's why it's considered least stable if you release more energy as you go from reactant to product. Okay, so I want to touch up on that because I didn't really talk about why they were more stable last time. I just told you it was. Okay, but are there any questions? You don't have to draw the orbitals. You don't have to draw this MO diagram, okay? So you don't have to draw this MO diagram where this axis is increasing energy of the orbitals. You don't have to draw that. But you should realize that these interactions is what kind of explain most of the concepts we've been talking about. Steric hindrance, stability of intermediates that don't have octets, and then alkenes is an extension of that. Okay, any questions before we move on? No? All right, so attendance been passed around. Make sure you sign in. All right, so we talked about E1. So alkyl halides can also undergo a different type of elimination. That's called E2. So it sounds like what mechanism we talked about before. What other mechanism had a 2 in it? SN2. So same kind of kinetics like the SN2, bimolecular. So it has to involve the collision of both your base now or slash nucleophile and your electrophile, your substrate. Okay, so I'm still trying to figure out the homework, the next homework assignment. I'm probably doing 2 weeks. It's all going to be about which mechanism is this reaction going through. SN1, E1, E2, or E1. Okay, and we'll talk about how do you decipher, how you determine between SN1 and E1. Okay, so but let's go over this reaction first. It kind of helps me tie in what I want to get across. So bimolecular elimination reaction. So this is called E2. Now there's another elimination reaction, but it has to deal with resonance. And we're not going to talk about that until next, if you're with me with 18B. All right, so there's another type of elimination mechanism, but we're not going to worry about that. Okay, so E2 and E1 are the only 2 elimination mechanisms we'll have to worry about. All right, so what if you have a good electrophile here? It looks like you form a carbocation, but your base here, your base is strong. You have a strong base, strong nucleophile, but you also, the concentration is increased, okay? So if you increase the concentration of sodium hydroxide, this actually doesn't go through E1 anymore, or SN1. It actually goes through a different mechanism, and it produces the alkyndo, the same product that we saw for E1. All right, so the products are pretty much the same as a SN1 reaction, okay? But here, the reaction rate is a little bit different, okay? So the reaction rate, it determines, well, it depends on a few things. So it's here. So here's my rate constant. That's something you determine in experiment. And then here's my electrophile, CH3, 3, CBr. All right, ran out of room. Sorry about that. All right, right here, just right, if you have room, guys, right next to here, put sodium hydroxide. So if I increase the concentration of my electrophile, the rate goes up, but also the higher concentration of hydroxide I use, the faster the reaction. Remember in SN1 and E1, it didn't matter. The concentration of your nucleophile slash base did not affect the reaction rate. So as long as you had a good electrophile in SN1, you could have used water, hydroxide, potassium hydroxide, you would still get the alcohol. And the rate would still all be the same because that reaction only depended on the carbocation forming. So that's the difference here. So by doing kinetics, we can actually figure out what's actually happening, and it gives us a more informed opinion on how to apply such reactions. So you're not like saying using chemistry as a black box and just guess and check. That's a waste of time, and it's not really scientific. It's more like magician type magic stuff, which we can debunk. Okay, so it's not like chemistry is not like magic. It has a very kind of scientific way to explain things. Okay. All right. So it's bimolecular like SN2. So let's talk about the mechanism. So there's a few things about this mechanism that we didn't really consider for E1 that you have to be aware of, and that'll be reflected in the next homework assignment, which I'm going to try and post today or tonight. Okay. Okay. So notice here I'm going to draw my BR and my H in a particular orientation. Well, in this case, they're all H's, so it doesn't really matter. But if this wasn't an H, if there was some other atoms other than H, you would have to rotate this to get it in this orientation, where the H and Br, look at the H in the plane of the paper and the Br. What's the relationship there? Yeah, trans, or if we're doing about Newman projections, right, in the anti-configuration. Okay? So this reaction is stereospecific. Well, I wouldn't say stereospecific, but it's conformationally specific. It's fastest if the hydrogen and the leaving group can adopt an anti-conformation. Okay? If it's not anti, either the reaction is slower. If it can't adopt that conformation, the reaction will be very slow, or it will just go through E1. Okay? All right, so here's my transition state, my H. Okay. All right, so I'm just going to show you the arrows. I'm not necessarily going to draw the transition state, but this is what's happening in the transition state. All right, so this is elimination. What's my base in the reaction? Is it sodium or is it hydroxide? Hydroxide. So if you see sodium hydroxide, just think, okay, sodium, just counter ion, floating in solution, not doing much. Sodium here is going to be free to do something. All right. So let's just draw the product here and see if we could draw the arrows. All right. So knowing the mechanism will help you predict the products as well. So you practice the mechanism and then try to do some problems where you guess the product. That will help you get a better understanding of how it works. All right. So here are my products. So if you look at the product in a mechanism type question, most of the time you'll be provided with the reactants, and then you have to provide how the reaction transforms, drawing some arrows, how the electrons are moving. And usually the product is provided for you. So as long as your arrows make sense, you will most often get most of the points. Okay? But now let's go over. So we have hydroxide. You notice here, the products are different. So do you think, in this example, is hydroxide acting as a nucleophile or as a base? Based on your starting materials here. And the products. Yeah, it's acting as a base, right? Because what is the hydroxide forming a bond to? If you compare this on the left to the products. What atom? H atom, carbon atom, hydrogen. So it's acting as a base. So what we do here is we draw our arrows right there. Okay, so if it's bimolecular, that must mean both of these processes, both the bond making and bond breaking, they have to occur in a single step. So there's 3 arrows that happen all at once, simultaneously. And this reaction is the fastest if the H and Br are trans, or I don't want to say trans, but anti to each other in a Newman projection. Okay? So this is the 3 arrows right there. All right? So if it's an E2 mechanism, draw out the reactant, the product, predict the product, okay? E2, alkene. And then here I just drew the most stable alkene, okay? So most oftentimes I'll specify the major product. See this alkene? That's the more substituted version. So this is why this one. This molecule is symmetrical. See, all the methyl groups are the same. So there's only one product, really. But oftentimes it won't be like that. Okay? So we have 3 arrows there. You get the product. All right. So there's a few things we should talk about this picture. All right. The transition state. Requires, or that's requires, okay? These 3 steps are necessary. All right. So remember, this mechanism happens is because the orbitals on each of these atoms, they are able to interact with each other. Okay. So I could show you pictures, videos, all these orbital interactions, but you just have to take my word that this reaction is feasible because the orbitals here, they can interact and overlap. All right. So every mechanism I show you and every mechanism that doesn't work, there must be some orbital overlap that's not possible in the reactions that don't work. So that's why we draw arrows a specific way. The orbitals are aligned. So I showed that very extensively for SN2, but I'm not going to show it for E2. Okay? But if you're curious, stop by my office hours. I can show you a video about that. Okay? So 1, what happens first? What's the first arrow I drew? Yeah, so there's a special name for a base removing a proton. That's called deprotonation. So first step is deprotonation. By the base. So it's not doing a nucleophilic substitution. Oftentimes, if your nucleophile can't approach the carbon with the leaving group and it's basic enough, the other thing you'll probably do is just go for a hydrogen instead that's nearby. So that's the other pathway nucleophiles can take. All right, so just like for a nucleophile, right? What happened to the leaving group? It left, right? As the name implies, it left. All right. So the second part is departure of your leaving group. Okay. And then what happened to the carbon? So usually, right, in SN2, SN1, the carbon didn't really change hybridization. It just, the hybridization went through a planar sp2 hybridization state in a transition state, but eventually rehybridized to what? sp3, right? But in this case, what's happening into here? Carbon's going from tetrahedral to trigonal planar, so it's actually rehybridizing to sp2. Very good. Thank you. So the two reacting carbons, they are going to rehybridize from sp3 to sp2. sp2 means trigonal planar, sp3 means tetrahedral. Okay. All right. So that's the 3 steps there. But now we can talk about what evidence supports this transition state right there. Why do they have to be anti? Why does the hydrogen being taken away has to be anti to the bromine? So there's support for this. So now let's talk about the support from experiment. So EXP here means experiment, okay? For the SN2 react, so not SN2, for the E2 reaction. All right, 1. In the lab, in the experiment, in kinetics, the rate depends on the concentration of both base and substrate. So rate depends on the concentration. So I'm going to abbreviate this. Conc means concentration. All right? Concentration of both the base, so hydroxide, and your electrophile, your substrate. All right. So the second part, the better the leaving group, the faster reaction. All right. So the better leaving group. So LG stands for leaving group. Results in a faster reaction. So what this tells us is that the CLG bond, so the carbon to leaving group bond, is partially broken. In the transition state. So that means there must be some bond formation also in the transition state. All right. So that's good. So the most important part is number 1, it depends on the base, and then 3 here, the base and leaving group. So the base here, in our case, hydroxide, and the leaving group. Sorry, I didn't mean to put a dot there. Are in the anti position in the transition state. All right, so we'll go over some examples to kind of prove this. So there's certain reactions you can do to test out your theories here, and that's how they determined these mechanisms. All right, are there any questions about some of these terms here? What I've drawn? Any questions about that? Yeah, Catherine.
So why is that for the transition state we have the bond between carbon and bromine a solid line when it's partially broken?
Oh, so here, let's just fix that. I wasn't planning on drawing the actual transition state, but we can illustrate what it looks like. So guys, just add some dashed lines to your drawing here. All right. All right, so that indicates there that the reason why I didn't draw it first is because I'm using arrows to indicate that. So I just want to make it a little clearer. But here I annotated a bit to show you what bonds are forming where. And that tells you that a hydrogen is being bonded to the oxygen from hydroxide. That bond to carbon is breaking to form the double bond between the central carbon atoms. And then to maintain the octet, that CBr bond, the weakest bond in this whole molecule, has to be broken, okay? So if you try this reaction with just, ethane, it wouldn't work because you can't, if we had a hydrogen there instead, okay, it wouldn't work because you can't break a hydrogen bond or CH bond or CC bond because you'll form anions that are too basic, right? H minus and C minus. So that's why it won't work. The leaving group has to be a good leaving group or a weak base when it departs. All right. Any other questions? No? All right. So let's do 2 examples. So the examples I like to use are cyclohexanes because those are they limit the possibilities of what you can write. But that's not important. So E2 reactions in cyclo. All right, so there's a few details I want to point out here because in the textbook and problems, they really don't point this out to you. This is something the instructor will have to point out. All right, so remember our chair structures. So don't forget about chairs. When you have a cyclohexane, we'll always use a chair. All right, So I'm just going to draw some of these bonds, okay? So the substituent is important. Now here's, whoops, I drew that wrong. All right. Okay. So you have two potential positions of these hydrogens. So remember, the hydrogen in an E2 reaction has to be one carbon over from the leaving group carbon to do it and form an alkene. All right. So in this chair, right, H and Br, what's their relationship? The ones that I have put a square around. This one and this one. So what's their relationship in terms of their conformation or their positions? Is it gauche, anti, or staggered? Sorry, gauche, anti, or eclipsed? Anti, right? They're not gauche because gauche would be 60 degrees. So that would be like the equatorial bonds. Those are like gauche to bromine. All right, so H and Br are anti to each other. So when you're doing this analysis, it's the easiest if the H and the Br are kind of towards the end of the chair, on the right side or the left side, okay? And you just have to write them in this both diaxial anti-relationship, okay? So they are anti to each other, okay? So if we now look down this position right here, look down through this carbon, we get this Newman projection. So I'm not going to write the rest of the molecule. I'm just going to leave this as cyclohexane. All right? So what this illustrates is that this is a bond to rest of the cyclohexane molecule. Okay? All right. Br is towards the back, so it's going towards the circumference of the circle. So hydrogen. Sorry, this should be hydrogen, not methyl. Let's put that there. Okay? And then this bond is on the other side of the chair structure. So that's why it goes that way. All right, and then in the center here, we have two hydrogens, so one pointing up to the right and one axial down. So see here, as long as the Newman projection tells you the Br and the H on the front carbon and the back carbon, they are trans to each other or anti, you will get this reaction. So this reaction is very fast. So I'm going to draw a line here. So let's just redraw the chair. Sorry, let's not draw the chair. Let's just draw it in the planar form because that's how alkenes are more stable. You don't want to draw them in the chair form. Okay, you could, but it's not common. All right. So that's the one position, and this alkene, it came from the opposite side. So we look at the opposite side here. No, it's all right. Let's see. The opposite side here, right here. And this side and that side, that's where the alkene formed. That's where the bromine was. Okay? So we get this alkene. So this reaction is actually really fast if we do these conditions. So fast reaction. And we have stage 3, O minus, sodium hydroxide, and methanol. So methanol here is just your solvent. All right. So to form the methoxide ion, you need to put in methanol. Okay. So that's how you get that reactive base here. So here I'll just put here, just to annotate, this is your solvent. So this is really fast. And that's because for the E2 reaction, the hydrogen and the leaving group are anti. So it's faster. Now, this won't be as fast if you do the other, if you have the other configuration. So say I have the same kind of chair, but the bromine and the hydrogen are not anti now. So we'll just do the same chair because this will lock the configuration to this being equatorial. But these hydrogens here, now there's a problem. We have now the trans isomer. The Br here is not in the anti-position with either of the hydrogens. Okay, so I'll show you how we can see that. So there are no H in anti-position to Br. All right, so we kind of highlight this bromine bond right here. It's anti to this one and this one. So what's the problem with that? Are those hydrogens? No, those are carbon-carbon bonds. Those can't break. Okay, so it has to be a hydrogen atom. So the only things that are anti to the bromine here are carbon atoms or carbon-carbon bonds. So this reaction won't go as effectively here. All right, so this is very, very slow. So much so that it doesn't even go at all. So we could usually just say no reaction here. So we try the same conditions here. You see that a simple change to the other stereoisomer does not result in any kind of reaction. All right, and I just left out the Br here and the sodium, just for clarity. I just drew the organic product. All right, so if we draw a similar Newman projection here, you'll see that based on our Newman projection, the H in the back will be axial up, right here. Your Br is now actually gauche to the hydrogen that would have been able to leave if it were an actual E2 reaction. And here's the rest of the cyclohexane. All right, so look at the Br here. The Br is trans to this, all right? So what we can say here is that this is a bond to C, not H. And the requirement is you need it to be bonded to H, okay? So that's why this reaction does not happen. So there's these kind of relationships we have to consider. All right, are there any questions on these two examples? So this is an example of a very fast, on the left here, very fast E2 right there. And on the right, very sluggish, not really going to work E2 for that one.
I just got a question on.
Yeah, go ahead.
The oxygen doesn't show up anywhere. Is it just because it's H2O and it's
Right, so actually what's actually happening is that if we just use this as an example, so here you're going to get more methanol. So what happens here is that CH3O minus, right? It's going to take H plus away from your chair, and it's going to just turn into methanol. So it just looks like it's more solvent. So that's why we do it in the same solvent, because then you limit your how you have to isolate your product. So that you can just now, since everything's methanol, you can evaporate everything, and you should get your product and a solid, which is like sodium bromide. So that's the other byproduct.
okay? Thank you.
Yeah. You also get, I'll just put here, when I say minus here, that just means this is a byproduct that also forms. Like that, okay? But you don't have to worry about that. What's the most important part is the major organic product, so the transformations that happened to your main reactant that you started with. All right, any other questions? Okay, let's move on here. So the question again will pop up. So when do we write E2 products and not SN2? All right, so this is the major skill we'll have to develop here while studying these reactions. So we're just gonna go over that right now. All right, because the goal here is to determine, okay, when do we know elimination happens? When does substitution happens? And what mechanism does it go under? E1 versus E2 for elimination, or SN1 and SN2 for E2? Okay. All right, but one thing I want to point out first is that, all right, SN1 versus E1. All right, so let's write a reaction for SN1. So terbutyl chloride, H2O. The product is you get OH plus HCl. All right, so in this case, 2 molecules in, 2 molecules out. All right, delta S here is 0. Does everyone know what I mean by delta S? Yeah, it is. What's S? It's not solid, so it has to do with thermodynamics. Do you guys remember entropy? So entropy means the more molecules you have, the more disorder. Well, we started with 2 and we ended up with 2, so that delta S is 0. So there's really no net gain in entropy. But what if we did elimination? Now, what if we had the same product, right? And then we added water, but we heated it up. So delta means this is heat. So it's interesting, when you heat this up, the product distributions actually flip. Your major product here now is the alkene, which is this guy. So you get that, okay, plus HCl, plus water out again. All right, so you're taking 2 molecules and you're actually getting 3 out. So delta S here, if we compare delta S is positive. Okay, so you can actually switch the reaction distribution, the product distribution, by affecting the temperature. And the reason why this is elimination occurs more easily, or the product is elimination at higher temperatures, is if we look at delta G again. So I didn't actually go over this in review, but the only reason we would mention it is here. Delta G is equal to delta H minus T delta S. So when delta G is negative, what does that mean? Is the reaction spontaneous or non-spontaneous? Is it non or spontaneous? Yeah, you got it. So this means the reaction is releasing energy. And that's naturally how things go, right? Reactions occur because there must be some net lowering of the energy of the chemical system. But if you have to input energy into a process, that's non-spontaneous because you're not free from external influence. You need to input energy from a force that is not natural and that was fabricated or manipulated a bit. So positive delta G will be non-spontaneous. Okay, so if we look at this reaction, right, when would delta T or delta G be most negative? We know delta S is positive. So in this case, the spontaneity of your reaction is controlled by temperature. So how will that make delta G even more negative? You heat it up, the higher the temperature, and that's why. Okay, so if you have heat here, think elimination. Elimination is favored. So if I give you the temperature and it's relatively high, say like 150, 200, 100 versus cold, 10 degrees, 25 degrees, is temperature favored. So high temperature, you favor elimination. And then SN1 here, substitution is favored at cold temperatures. In this case, room temperature, that's not really considered hot or warm, so that's still considered cold. It's just all relative here, okay? Because it's all relative. So a cold reaction compared to a high temperature reaction, you have to make a comparison. So for example, negative 40 would still be considered cold versus 25 degrees because that's relatively higher than negative 40. Okay, so it's not like a number range. It's always relative to something else. Okay, so that's why I want the distinction I wanted to make, because you'll see reactions with no heat sign, and you'll think, okay, SN1. But if there's heat involved, you should think, okay, E1 is our major product because of entropy here. All right, so you don't have to worry about the equation per se, but you should think, okay, if I have positive entropy and the reaction is more favored if it's increasing temperature. Okay? Are there any questions about that? It helps to practice, okay? So we'll do some practice as well, or on the homework. Okay. All right, now we have to determine when does E2 occur predominantly. So when does E2 occur? So predominantly means as the major product, so as the major mechanism that produces the alkene. All right, so there's a few different areas here. One, sterically hindered substrates. So which ones will be sterically hindered? Primary, secondary, or tertiary? So your two main culprits here are secondary and tertiary. So let's put that in parentheses, secondary and tertiary. Because if the nucleophile can't approach your carbon, then it's going to go to the second next best thing, a hydrogen atom that's close by, but that's not necessarily blocked. Okay, so that's the whole point of the the mechanisms we showed. E2 happened because the hydrogen was more accessible than the carbon atom in the center. Good. So in reaction so here, your nucleophile has to be strongly basic. So with strongly, and I'll give you some examples. So strongly basic nucleophiles. All right. So examples are, all right, CH3 minus, so R minus. So let's do R minus. So any carbon group. H minus, OH minus, so hydroxides are strong base, alkoxides, well, just an R group, strong base. NH2, so NH2 minus, very strong base, because you can kind of see that all these reactions, or all these nucleophiles, they are the most basic ones on the periodic table. So it's not large atoms. Large atoms won't do this. Like iodide won't do that because it's not a very good base. So it's all the ones in group 2, really, and hydrogen. Right? All of these elements right here, these are good nucleophiles, very good nucleophiles, but they're also, if they're charged, very good bases. So we have to be careful here. Okay? So the smaller the ion is, so remember atomic radii, the smaller the ion is, the more likely it'll prefer to attack something small. And that's a hydrogen. Okay? There's a whole acid-base theory about this, but I didn't mention it. Because it's kind of complicated for here. So just think, Small ion prefers smaller, partially positive, or smaller atom. So here, if it can't approach the carbon atom, it will choose hydrogen because it's small, like these ones are. Okay? All right. So they will favor E2. So remember, like I said, SN2 or E2? Well, if you have a strongly basic nucleophile like this, it will go with E2. So let's do some examples here. All right. So we have a sterically hindered primary bromide. So notice here, I'm not even specifying the heat here. You don't have. Well, it's not important. So CH3. All right, so let's think about it. Well, is our substrate hindered? I mean, I said it was, but do you agree? Yes, because look at the opposite of the leaving group. There's those two methyl groups that you have to approach. That will cause steric hindrance. Some unfavorable Gaussian interactions. All right, so the product distribution, you actually get a mixture here. What you should do, if you see this on exam, what you want to write is just the major product. So as long as, based on what you learned here, as long as you recognize that it should be E2, you're going to just write the E2 product. All right, so this is actually 60% E2. And the corresponding SN2. So remember, as long as the back carbon here is not tertiary, you still get some SN2 products. It's just very slow. All right, so there's my OCH3 right there from this guy right here. Okay, so that's how we got that product. All right, so you only get 40% of this product here, so SN2. All right, so which one's major? E2, because higher percent yield. All right, so these are actually percent yields. So this is product distribution, but this is based on yield from your starting material. So if you had 1 mole of your starting bromide there, you only got 0.6 gram or 0.6 moles of your alkene and only 0.4 moles of your ether there, that substitution product. All right, so let's do one more and we'll take a little break here. So let's have now a secondary bromide. Okay. Now I'm just going to write this nucleophile a little different. I'm going to use the alpha version, so sodium ethoxide. All right. So sometimes I won't write these charges out, so just know that they are charged, okay, in solution, OH. So you notice here, every time we use an alkoxide, the solvent is almost always the acid, the conjugate acid of the base. And that's because if you put something else in there, it may react with that, okay? But if this alkoxide reacts with an ethanol molecule, what do you get out? Anyway, you get the same charge, right? So it doesn't matter. So that's why the solvent is this. If I choose methanol might be deprotonated by your negative charge there, and you'll get methoxide too. So you have two different types of nucleophiles now, and that causes problems. All right, so you have to be careful with that. Okay, so now this one, the difference in this one, this carbon with the leaving group is secondary. So now your percentages here are going to be even more skewed. So you would get E2 again. But it's going to be even higher. All right, so 87% now of E2. So these are just some examples we've chosen. All right, and then you have SN2 products here. Your asymmetrical ether, only 13% of SN2, so very poor reaction here. And Since you got mostly 87%, that's a pretty good reaction. You can separate these by distillation. Okay, so it's very, very easily separable. I would think one of these has a very low boiling point, so you can just evaporate one off and get your final product. All right, that would be the goal. Okay, so let's take a little break here, 10-minute break, and then we'll talk about the other instances where E2 is favored. And then we'll talk about predicting substitution and elimination, all right?
Can you open the assignment, the look at assignment? It doesn't let me send out pictures.
Can you leave a comment? Try to leave a comment.
Okay, I can try.
Yeah, that's smart. I would say that so everyone so it's like, oh my god. And I didn't do that.
I didn't tell you. No, they hadn't told me. Like, I also didn't know unless one was told me because the other one was just shit about it.
All right, looking at that.
They've been acting weird.
Yeah.
We're in a mobile way.
But here, just like,
No, I've done no
no one's like
tricks.
shared around, like, together, whatever. But like,
Based on what, you know.
Tara, the one before that they broke up, she has a smaller room and she has nothing. Then that dinner Friday after she told me.
Last question, what was the last
she moved
question?
all of her stuff.
Oh,
out of
she
the
was
locker
what
in the
more
back
stable?
room. From Maddie's room into her own room. And like, it bothered me because like,
Oh, that one.
if Tara and I weren't dating, I would have had to share stuff with Tara because I felt her about there, but because Maddie and Tara were
What?
sharing the master bedroom, I would not.
We did.
Oh, now she asked you.
So I had to make stuff this weekend and figure it out. There was also awkward shit because like
Yeah, this one we didn't talk about
so many
S1,
times
so there's only one
like they would be like
just soft.
Maddie would want to do something by herself and Tara would want to do something by herself.
Backside.
It happened wrong.
Throw your arrow from
From
the
very
opposite side.
good.
Leave your group leaves at the same time.
One of them would go nap and then so would the other. Like, that's so amazing. Like, I was not going to make my other half and I didn't know.
Oh, I'm so, that was my next question. Do you have an additional?
Yeah.
Okay.
No, I didn't tell her. I was like, I told her because like, I'm never planning to be your housemate and she know. Like, yeah, years in front of like, but I was like, they have to let me know. But I'm not pretty sure. And she's like, I told her she was going to notice. She's like, oh.
This is comprehensive. You felt.
And I was just like, it's just weird. Because like last night, I worked, I took work like the entire shift from 5 to 11. For that. But like normally, like my husband's don't really care about my schedule because they like, you know, they're like, oh, this is my friend, just go to work. She's not for that. And then like Terry will be like, oh, are you coming back tonight? You're working the whole night. Like, I was like, yeah, coming back at 11. What happened? Like she never answered it. Mind you, when I left for work, Maddie had gotten home. But when I got back from work, Maddie was not there, and she didn't come back either. The dog was there, and her dog was named Tara. Tara and I was like, what's going on?
Yeah.
I'm like, that's something.
Right.
Like, I don't want to deal with this right now.
I know, it's such a, I had the same situation when I lived with 3 other girls in Chico. And I thought they were just best friends, but they actually were dating. And they broke up and I shared a small bathroom with her. It was like a makeshift bathroom that they added onto the house. It was so tiny.
Wasn't my bathroom like, is it tiny, but it's like, I have a lot of shit.
I bet, I was gonna say, you probably have
Because I
so
have
many
like
things.
hair products and skincare products, so like I bet stuff so I have easily distributed in all the drawers and then I can move shit around and make things better and then plus other stuff. It's like, luckily I do have like the majority of the space, which is nice. Like she doesn't have too much stuff, which is good. but it's still, I feel like it has some like
Guilty, yeah, she has space. But oh my gosh, it's so bad. Just the vibe, like when you knew there was some tension, some awkwardness from previous.
Yeah, like I wonder what the things going on, but it's just like I wonder what she asked to tell you anything back. I'm gonna ask. I saw her. Maybe she wanted to leave or something. But now it's clear. I'm like, what? I talked to me about it.
Right, they can tell me stuff.
Yeah.
Whenever people are like, you need to talk to a person. I'm like, worst case scenario. I'm like,
I want to puke. I literally, I always
or like when people are like, people are like, you need to talk. I'm like, what?
What did I do?
I'm like, what?
I had such a, I'm doing nights, I'm almost done, but it was really good until last night at 4 a.m. This guy ran in with his baby, he was like 18, his baby was a year old, and he was actively seizing. He was actively seizing for 30 minutes. And so they shot him up with Ativan and Keppra, and that's like pretty good seizure medication. He really stopped. And it was the scariest thing. I like started to like panic because I was half alive and I saw this baby and I was freaking out. Then I started crying in the bathroom and you could tell I was crying and he's like, it's okay, we're trying to see the patient. I'm like, it's just so scary. Like you wake up in the middle of the night and your baby's like that.
Especially for you.
Yeah, so I was like, and then I was telling him, I was like, I did not, because I feel so guilty, but I let him stay because he sleeps with us, but when we do nights, like I have to sleep, so I put him in his room after he's like fed, and I get up every 2 hours, because he'll get up every 2 hours, he'll take a nap and get up, and I was just like, I told my parents what happened, I was like, can you please keep him for 6 hours, and I'll come back again, because I feel so guilty. He loves his toys in the room, like nothing can choke, he can't choke on anything, but if he starts seizing out of nowhere, that's exactly what that kid did.
Oh, good. I'm sure. All right, everyone sign in. Where's the pen?
Dude, your mom would be a like that's.
I wasn't addressing you specifically.
I signed this for all the time,
We were old enough to
In my 2A, I did that yesterday. Because people would like leave class like after 20 minutes. But here I have, I don't. Yeah.
That's so true. Like they
Sometimes there might be something to do with class that that blends to my here. Minus that. But I haven't done that yet.
Like, they were fine with like the beans, the small ones that were.
But you remember back in the class, took a tour all day, right? Got extra credit. That was. Hey, stick around. We got perfect attendance.
Just because I overwhelmed 50 points.
No. 50 points.
Oh my god, Jackie. It's so fun. It's so much fun. It's a trampoline land and someone is sad. I'm just going crazy there.
I didn't move it yet. It's still 0%. I haven't finished it. I will. Yeah.
Don't wonder, I said about it.
And that's
true. Oh. That's so funny.
because it's like around the
Yeah. Well, that update me on the
What's the T?
Outside of mine, I've been dating for almost 4 years.
Oh yeah. And they broke up.
Yeah.
Damn.
And
Wouldn't want to come back there.
I don't know what caused it though. We don't know what caused it, right? Because they've been totally normal. So we don't know what caused it. We don't know what happened. And they're like currently in the gray area. We're not really sure if they're fully broken up or just like on a break.
Break, yeah, right. Oh man. It's really awkward.
Because I'm the mediator.
Yeah, right.
And it's like both are like, because now like, both of them have like their own separate rooms. But like, we're all in the same floor area. So it's like, there's like we're sharing everything, and they're all so close. So it's like I'll get up in the morning and like people have woken up and they're talking in the hallway, and I'm like, are you going back to sleep?
Yeah. Yeah. Damn. Well, hope they figure it out.
Andrew, today or over the weekend at my job, they ordered this medication that had methyl. It's like a breathing treatment. Not taking from notes. It's SOLON.
Yeah, it's probably a steroid.
Yes, but it was so weird because I've never seen methyl on a medication.
Yeah, so you think about like steroids sometimes, especially like the hormone type of things, they have a ketone in it. Yeah, and then they add enough group, it changes activity. Different hormones, yeah. All right, so let's get going here.
There's like, oh man.
All right, so the other possibility, what if your substrate isn't hindered? What's the other thing that can potentially cause elimination? So if your substrate's not hindered, what else could be potentially hindered? No, so that's like the only other thing that won't be hindered. But sometimes your nucleophile, right, could be branched. For example, so here we have bases. All right, guys, let's settle down here. Sterically hindered bases or nucleophiles. So what happens here? Your nucleophile. All right, guys, slow down. If your nucleophile is sterically hindered, it will not be able to approach. So it won't be able to act as a nucleophile anymore. It'll favor acting as a base. So favors elimination. All right, in this case, E2. All right, so let's do an example. You have a primary alkyl bromide. So now, in this case, I'm going to put my base as a sterically hindered one, all right? So this one is called tert butoxide. It's very similar to methoxide and edoxide, but now it's sterically hindered, so it's CO minus K plus. And the solvent here underneath is just the conjugate acid of your base. Okay, so my carbon group is now sterically hindered. I have multiple substituents on the same carbon. That creates branching. And what I get instead is this group here. C. So my alkene here is my major product. So you get 85% E2. And then only 15% of your desired SN2 product. I don't know if it's your desired, based on what you want, okay? So the only time this base won't act as a base is if you had something like methyl bromide. Methyl bromide, you can't form an alkene, right? Because there's only one carbon atom. So you'll actually get SN2 with very bulky nucleophiles, only in an SN2 fashion with methyl leaving groups, so like methyl bromide, etc. Well, I mean substrate, methyl substrates. All right, so you have to be able to identify. Look at your nucleophile. Is it basic as O minus, N minus, C minus? Basic, very basic. Then you have to say, okay, is it sterically hindered? Is it bulky? If it is, E2. So that's one of the bases you may see. I'm going to draw a few others. So you can have the sodium salt of this guy. So if I put Na plus, no different reactivity. Now, some other bulky bases you might encounter are these ones. So other... All right, triethylamine. So a very common base in synthesis is triethylamine. All right, so another related amine, this is called, it has a very particular name based on the person who made it and popularized it in chemistry. So this is called N, N diisopropyl ethyl. So there's two isopropyl groups and one ethyl amine. All right, this is called Hunig's base. So you have this type of U. So if you want to do elimination, oops, sorry, I didn't mean to put that. Put parentheses. Sorry, not parentheses, quotation marks. So these are uncharged amines. And then there's one more amine I want to draw. It has the name DBU. Okay, so it's a cyclic compound. All right, so let's practice drawing here. So we have a 6-membered ring with 2 nitrogen groups. All right, now bear with me. You're now going to draw a 7-membered ring. Boom. All right, you will never have to draw this out because I will abbreviate it as DBU. So this is commonly known as DBU. And here's how you name it. 1,8 dash diaza. So aza is a naming organic for nitrogen. Bicyclo. So bicyclo means you have a ring system, but you technically have 2 rings in there. There's 2 different sizes, and they're fused. Okay, they're fused together. So bicyclo, and then in parentheses, we use a numbering system to indicate the size of the ring by counting the distance away from the fused part. So 4-0. Okay. So you don't have to worry about this nomenclature. And then the last part is unde 7. All right, so you kind of see how complicated, the larger the structure is, the more complex structurally it is. The naming gets even more complex. Okay, so that's DBU. All right, so the ones we want to worry about here are DBU you might see, but this is the other common one we'll have to recognize. So this is LDA. So diisopropyl, lithium diisopropyl, and lithium is commonly written nearby because it's a salt. So this is called lithium diisopropyl amide. So this has the abbreviation as LDA. All right, so you see LDA as a strong hindered base. So it's a very effective base in organic. All right, and then one more. There's another amide we commonly see here. So let's do one more here. Now you have silicon groups. So silicon groups are also particularly electron rich. They're like carbon. So here's the first instance we see silicon here in organic. All right. Boom, boom, boom. So these are methyl groups. Sorry about that. So it's very similar to LDA, but LDA is stronger based on its pKa. Sodium here. So this would be called, so you have sodium, lithium, potassium, doesn't matter for our purposes. So sodium bis, trimethyl-silyl. So that's how you name the silyl groups, the silicon groups. So trimethyl-silyl, because it's silicon, amide. So very similar to LDA. So we don't say this. We usually say sodium HMDS. So hexamethyl disalicide. All right, so HMDS. So that's also a strong bulky base. All right, so we as chemists, we can actually take advantage of these reactivities and we can apply them towards targeted synthesis. So that's the whole point of synthetic work. All right, so these are the bulky bases. I would say focus on this one, LDA, no LDA. And then DBU, triethylamine, those are all also common bases we use. So if you see DBU, just think bulky base, okay? And the other one here, terbutoxide, the one I showed the example with. All right. Okay, so we can also draw potential energy diagrams for E1 and E2. So very similar to how we drew the reactions for SN1 and SN2. But we won't worry too much about that. Okay, so just imagine for E1 and E2, you can also write potential energy diagrams. But now we want to kind of talk about the competition between SN1, SN2, E1, and E2. Okay? So now let's do a different section here. Okay. Well, maybe we'll do something. Yeah, let's do it. All right. Let's just draw them anyway. Potential energy diagrams. All right. So this will be my reaction coordinate. So reaction coordinate. So let's say this is for E2. And here's my energy. As the energy increases, so does the instability of the products of the things here. All right. So we have our terbutyl. Oh, that's my bad. Br. Plus OH minus. These are my reactants. And right here are my products. And right here is the transition state. Okay. So in E2, what's my product going to be? Substitution or alkene? The alkene, right? So HH. Get the two methyl groups here. And we get our Br minus plus H2O. All right, so in my transition state, we have two carbon atoms here. Oh, sorry, let's go back. Erase this double bond. We need to show that's forming in the transition state. Okay, the hydrogen here is breaking down. OH minus is interacting with here. So we can actually turn this negative sign into what kind of charge? There you go, thank you. Partially positive. And then this bromine here, partially negative right there. All right. And then these hydrogens are nothing's happening with these hydrogens, so let's keep them the same. All right, so this is my transition state. No, partially negative now, because now it's going towards forming water. Yeah. So partially negative. Good. So the negative charge now is dispersed through the whole transition state. So that's why we use polar solvents to stabilize the transition state, faster reaction. And now we get this situation here. So overall, this will be negative. Okay. So that's for E1, E2. How would E1 look different? Now let's think about E1. Well, this is one step, right? How many steps was SN1/E1? 2. Oh, well, it's technically 3 for SN1. But what about for E1? It won't be 3, but it won't be 1 either. 2, yeah, because you had first the carbocation forming, right? Then you form the alkenes. Let's draw that. All right, so I'm going to draw like this. All right, I have my products here. My reactants right here again. So very similar for reactants here, starting with the same reactants. But the only difference here is your nucleophile is a little bit different. So we use water here. For E2, you can't just use water. There'll be no reaction. It'll be an SN1, E1 situation then. But if you use hydroxide, the mechanism changes. All right, so let's go to the first transition state. So what happens first here? All right, so this carbon atom, the bond to bromine is being severed. So you're forming a partially negative and a partially positive on the carbon atom that's breaking, or that's being formed, the bond that's breaking there. All right. Boom, boom. So this is my first transition state. All right. Well, this is elimination, right? So this second part, this should look, this transition state should look really similar to this one we just drew here. Well, what's the only difference in this case? One, we have a carbocation. And then what's the other thing that is going to form here? All right, so let's draw our hydrogens. Anyone? Yeah, double bond, right? So this one will have a partially positive charge because it's a carbocation. It's losing that partially positive charge. So here, boom, boom, boom. All right, well, that's not where the partial positive charge is it? Sorry about that. All right, so the partial positive charge is right here, right? On this carbon, where all the 3 methyl groups are. All right, well, this carbon is now forming a bond, double bond character here. And then this H right here is going to be breaking. So this H is going to form a bond with water. Now water is going to be forming a partially positive charge because it's gaining a hydrogen from the carbocation. So boom, boom, bada boom here. So this is where my transition state now has a positive charge. So that's why it can also be stabilized by a protic solvent because it's charged. Okay, so this is my second transition state. All right, so for potential energy diagrams, you know, if I ask you about the mechanism, be able to draw out the intermediates, the species here, and then the products. So I'm missing one thing. Which peak or valley did I label? Did I forget to label anything? So what's the intermediate structure between the first and second transition states? What is that called? Yeah, carbocation. So the only difference between these two mechanisms is one has an intermediate, a carbocation, while the other does not. So there's a plus charge there. Well, sorry, it's all right. Let's write it at that. Plus charge on this carbon, plus Br minus. So those are our two. Everything has to be neutral as it started, so that's why we have to include the charges there. And the end product, it's not necessarily charged because I neutralized, and that's because I didn't put the Br there. Okay, any questions about that? All right. Okay, so we're kind of wrapping up our discussion here about reactions of alkyl halides. So now we have to differentiate all the different mechanisms. Which one is it? E1, E2, SN1, SN2. There's a few criteria here that we can go and talk about. Okay, but are any questions on these graphs? Any questions so far? No? All right. All right, so competition. Substitution. So there's a lot of resources, not just here, online and textbooks, about the differences here. So for this chapter, I put a reference guide on Canvas under the handouts, and I posted a lot of other handouts about pKa's, nucleophiles, what makes it a nucleophile. And then I did a few-page document here about difference between substitution and elimination and all the factors that influence it. So if you need a more pictorial representation of that, I did make a document for you guys. Okay? And that's because what I'm going to talk about here, it's a lot to kind of go through. So you have to start early and, practice this, okay? And that's what the homework's going to be for, in part. All right, so the first point I want to make, number 1. For weekly basic, nucleophiles. The major product. All right, well, in the major product, what do you guys think? If it's weekly basic, do you think that's going to act as a base? No, so what should the major product be? Elimination or substitution? Substitution. So that's how we do it. All right, so I'll give you an example. What are weekly basic? Because if I don't tell you what nucleophile is weekly basic, you might be confused here, okay? So the thing we say here, bases weaker than hydroxide. So there's a table that handout I was talking about. There's a table of pKa's. So if the pKa is lower than 15 or 16, that base is more nucleophilic. Okay, so anything less basic than hydroxide or basic water. All right. They give good yields of SN2 products. With primary and secondary substrates. All right, with tertiary, the predominant mechanism is SN1. All right, so if you have primary and secondary, it'll be SN2. And with secondary, for the possibility of, stereo centers, that's where it'll be inverted. Okay? All right, and then here I want to say SN1 products with tertiary substrates. All right, what are some examples of these type of bases? All right, so let's highlight this. So we're weakly, basic. All right, so here's some examples. I minus, Br minus. Cl is in there too, but it's not a great nucleophile, so I didn't put it here. Rs minus. A nitrogen atom that's not sp3 hybridized, azide. So the reason why azide's good is because it's charged. It's charged, it's delocalized. So that's why it's not a strong base. All right. So any carbonate, so like acetate, okay, and PR3 are good examples. Good nucleophiles that give mainly SN2 or SN1 products. So mainly substitution. All right, so let's do some examples here. All right, so we'll have to be able to classify something that's weakly basic and strong basic. All right, so let's say we have this situation. All right, sorry, that's a bromine. Sodium plus iodide minus. So, all right. All right, so what should major product be? Well, I have secondary haloalkane. My nucleophile is weakly basic. And my solvent is that polar protic or polar aprotic? All right, it's polar, but is it protic or aprotic? Yeah, aprotic, no OH or NH bonds, right. So our main mechanism here is SN2. So you're going to think it's SN2, so we get iodide here plus sodium bromide. So this reaction is so good, it's 100% yield. All right, and then the mechanism you would put here, SN2. All right. Now, another example. Let's take the same bromoalkane, and instead we're going to react it with a weaker nucleophile, and that's going to be acetate. All right, so the only difference here is we substitute a nucleophile. It's still weakly basic. Everything else is the same, solvent, substrate. So you would still expect a, let's see here, what I want to write. You're still going to expect a SN2 reaction. All right, plus sodium bromide. This one is also pretty good reactivity here, product-wise. So you get 100% of this product. And by 100%, I'm not talking about the sodium bromide. That should automatically just give you 100%. I'm talking about the major organic product, so SN2. Okay, so these are both SN2, and And now I'm going to show you example SN1, some SN1 examples. So we're going to have a tertiary bromide reacting, whoops, sorry, erase that. Sodium azide, so that's N3, with methanol. Okay, so my nucleophile is weakly basic. My solvent is protic, methanol here, right? But my substrate is tertiary. So I would think substitution, right? But which one? SN1 or SN2? Yeah, SN1, right? Because you have a tertiary substrate. So you're going to get primarily this product here because this is your better nucleophile. You're still going to get some solvolysis. So solvolysis is basically substitution by the solvent. So still from OCH3. But it's going to be minor, and that's because which one is the better nucleophile? The one that's charged on the more basic nitrogen, or the one that's neutral using oxygen? The charged one, right? So it's clear as day there. All right, and then as always, we didn't specify a temperature, so you don't keep it cold or hot. You're going to get some alkene minor product. All right. Okay. Number 2, weak nucleophiles react with secondary and tertiary substrates elimination is a minor side reaction. So side reaction or side product, that's something that's produced as a different reaction takes place. A byproduct is something that's produced in addition to your major product. All right. So the example I want to put here is my secondary bromide. All right. So here I'm going to put water, methanol. So remember this temperature, I'm just going to put temperature here, but it's all relative. So this is actually the cold situation, okay? So this is just an example, just for example, okay? So I would get the SN1 product, my 3-pentanol. So this is 3-pentanol. You don't worry about that name. So 85% of my symmetrical alcohol, so SN1, but only 15%. So you still get a minor elimination product. Okay. Now, if we did this even colder, this reaction might occur faster, but this probably is the best you can do because if you decrease the temperature, this carbocation that forms is on a secondary carbon. It's not as good as tertiary. Okay. All right. And then the third criteria here. But are any questions on these two examples we went over? No? All right. So let me just scroll up a bit. So we talked about weak nucleophiles, weak bases. This is this situation. Weak nucleophile, weak base. The first situation was good nucleophile, weak base. All right. This is both weak nucleophiles, weak bases. All right. So a good nucleophile can either be a weak base or a strong base. A weak nucleophile, the only thing it can be is a weak base. So this is this example right here. All right, to wrap up things for today, we'll go over the third point I want to make, and then on Thursday, I'll create a little chart to help you determine which mechanism it is, okay? So, and then we'll talk about alcohols on Thursday. 3, strongly basic, unhindered, so this matters, unhindered nucleophiles. So if it's unhindered, what do you guys think it favors? Is it going to be SN2 or E2? Elimination or substitution? Right, because it's not unhindered. So substitution. But this is only saying if the substrate is methyl or primary. Or primary specifically. Okay? With methyl groups, you can't do that. You can't even eliminate. So with methyl, but it has to be unhindered primary. What happens if primary is hindered? Exactly. Good word. Yes, that's right. So here I wanted to make some few points. So substrates at low temperature. So it has to be low temperature. Okay? My example is propyl bromide. React that with sodium hydroxide, so a strong, unhindered base. And the solvent is always methanol. Okay? The solvent doesn't actually have to be methanol, but in most cases it always is because it's hard to get sodium hydroxide as a solid. It's very unstable. Okay? So, your two products here, are. All right, first you have your alkenes. So imagine I draw the alkene from the center here, right? And then the bromide is leaving. Like this. So, only 9% E2. And then here is a successful SN2 one, okay? So 91% SN2. So you can really drive these reactions forward based on the parameters of your reaction. Substrate, base strength, hinderedness on the base, and then hinderedness or, substitution pattern on the substrate. You can really get one product. So this is a successful reaction. 100% would be better, but oftentimes that's not practically realistic enough to be done in the lab. All right, so that'll be it for today. Thursday, we'll wrap this up and start talking about alcohols. Okay?